Hello, everybody. We're now going through Objective 5, which is knowing how to find the cutoff points on the t-distribution. This is step 3 in your process, and it's really similar to everything you've been doing before. It's just that the t-distribution is a little bit different. The t-distribution, the cutoff points vary depending on the degrees of freedom or the number of people in your sample. So if you have a really small sample, it's going to be it's going to be a cutoff point that's more stringent, more to the extreme of the tail than if you have a sample size that's approaching 30. So I'll show you how to look these up today. You can see that we're using the same kind of information. We're using the significance level, 0.05 or 0.01. You'll be familiar with that already. But what you might not be familiar with is we've been calling it significance level or p-value, and both of those are correct. It's also called alpha, and it's written out as this sort of italicized, little bit curlier A. So A equals alpha, which is the same as significance level or P. So in other words, if we say P and say we want a probability of less than 0.05, we're looking to see if there's only a 5% chance of getting that score if we just selected a sample at random. So P equals 0.05 is a 5% chance of obtaining a score. All right. Alpha is just another way of saying it. It's saying that's going to be our cutoff point. Okay, our cutoff point is going to correspond with that 5% chance. So it's all one way of saying the same thing. And I'm telling you all this because you're going to see these words written when you look up your cutoff points. And this is the other new phrase you're going to have. It's critical value. Critical value is just another term for the cutoff point. So if we have a cutoff point of 1.96 when we do our z-scores, we could say cutoff, or we could say critical value. And in the app you're going to be using in this step, they're going to say critical value. And they might even say critical region. And the critical region, if you see that, region, we've been calling the shaded area. So that's just a little bit of familiarity with what we're doing. So in this case, there's only you need a couple of pieces of information only. You need to know the N because you have to calculate degrees of freedom. You need to know alpha, which is again, the same as the significance level. And you need to know the tails. And of course, what side of the tails they're looking on. So all of this is exactly the same of what you've been doing. It's just that we're going to look up the different critical values using a chart. So you could use the back of your book. That's what your book, in fact, recommends. I actually prefer to just go, now that we have resources online, I prefer to just go online to do this and use this, something like what I'm showing you here. This is a nice one, and I've given you the link. And it's just to use a little calculator for us. So this is a T critical value calculator. The T stands for we're using the T distribution, and that's that distribution that's based on those estimated spread indicators. And this is our critical value calculator. So all you have to do is enter your p-value or alpha and the degrees of freedom, which is n-1, sample size -1. So in this case, our p-value was indicated as 0.01, alpha 0.01, and n was 26, and we're looking for one-tailed high. So in this case, we don't have to change our p-value. It already says 0.01, which is what we're looking for. N is 26. We know that we have to enter degrees of freedom, 26 -1, so we have to enter 25. And now let's see what happens when we hit calculate. It tells us critical value of T right-tailed. That means one-tailed high because if a one-tailed high, we're looking for that value on the right side of the distribution. The critical value or cutoff point in the one-tailed high is 2.49, which means that we are looking to have a t-score, which is sort of like a z-score, more than 2.5 standard deviations from a mean. In other words, we're looking for a sample t-score more than 2.49 standard deviations above mean. So we're looking for a score that's pretty far out in the tail. That's all you need to write, though, is our critical value. Next, we have n equals 50 and alpha at 0.05. So let's pull that up again. Alpha 0.05, let's change this. Degrees of freedom 50 is our n, 50 minus 1 is 49. Let's calculate. And what tails were we looking for? I forgot to check. Oh, two-tailed. So what is the cutoff point or critical value? Well, critical value of t, two-tailed, is plus or minus 2.01. That means that we'll write down plus or minus 2.01, and it just means that we are looking for a value in either tail with the cutoff point of 2.01 on the high end or minus 2.01 on the low end. Next, we have n equals 16, alpha equals 0.05, one-tailed low. So let's go in and look at our calculator. It was n16, alpha 0.05, one-tailed low. So alpha is already set to 0.05. 16, n minus 1 equals 15. And we're looking for one-tailed low. And so here's our critical value of t right-tailed. If we're looking on the low end of the distribution, which we are, we just put that minus sign in front of it. So if we were looking on the high end, it would be 1.75. Because we're looking on the low end, we just need to have minus 1.75. So let's write that in. The critical value is minus 1.75. And all this means is that we're looking for a value in this lower end of the distribution, and it's got to be lower than minus 1.75 standard deviations from the mean. If it's lower than that, then we have a significant difference. And this is our last example. N equals 35, alpha equals 0.01, one-tailed low. Looking at our calculator, we're doing another one-tailed low, but we were looking at, it's a hard time remembering, 0.01 and 35 for the n. So let's go ahead and get our calculator up. 0.05 and n 35. So we have n minus 1, 35 minus 1 is 34. Let's calculate. We're looking again at one-tailed low, and I'm having this fear that I just want to make sure that it was in fact, it's 0.01. All right, so it's 0.01 in this case, and let's change that. 0.01. And 34 is correct. So let's calculate again. And we can see that if we have 34 degrees of freedom and we're looking for only a 1% chance of coming up with that result from a randomly selected population, that the critical value of t is going to be, if it was right-tailed on the high end, it would be 2.44. But because we're looking on the low end of the distribution, it's going to be minus 2.44. And that simply means that we are going to look for a score that falls in the low end of the distribution, and that the score is going to be lower than minus 2.44. And if we find that, then we have a significant difference. And that's the end of this demonstration.